Okay, there is a very deep theorem, and I'm just going to write it, and I'll give you a reference for all this material later because I haven't defined those terms. So a category C has filtered colimits if and only if it has directed colimits. Very deep theorem. Yeah, the proof is hard. I cannot cover it in this course. Yeah, so basically, the thin diagrams themselves are sufficient to control all filtered colimits. Okay, so now that we have established this property, we can always talk about directed colimits and filtered colimits alternative. I mean, in any way we want. Usually, these directed shapes are the ones which we need. Now, here comes another definition. So, given a diagram D from I cross J to C, we can form this particular limit, lim I d I blank. Yeah, where will this lie? This particular object, the limit of shape I. Exactly. We can form this. So this is a diagram from J to C. And because it is a diagram itself, we can again take its limit or colimit as we wish. Okay. So, and similarly, we can do the other thing. Yeah, first take the colimit in shape J, then that will be a diagram of shape I. It will not just be one functor, but it will also be some natural transformations because originally we are given a diagram. Yeah, you understand that. Yeah, so therefore, indexed by objects of J and together with all natural arrows between them. Yeah. Okay. So therefore, we can take their colimit, and so we can form the colimit of shape J of limit of shape I of D. Okay, so we say that limits of shape I commute with colimits of shape J if this following diagram commutes. Here we are starting with I cross J to C. Then from here to here we have JC. From here to here we have IC. And from here to here we just have C. Obviously the maps are clear. This is lim, then this is colim. This is colim, and this is lim. If the diagram commutes up to a natural isomorphism. Okay, of course, I mean, when we are talking about diagrams of functors, we cannot expect that they commute up to equality. They have to commute up to natural isomorphism. I mean, limits and colimits are not spatial here. You can also show that limits and limits commute with each other, but that's always true. And that's one of your assignment problems as well. Yeah, show that limits always commute with limits if they exist. Yeah, I mean, okay. Yeah, okay. Maybe I should write a note here. We are assuming that all appropriate limits and colimits exist in category C. Yeah, this one we are assuming. Obviously, without that, we can't take the limit of a diagram, take the limit of a colimit of a diagram. So we are assuming their existence. So, I mean, just for the sake of completeness, let me write that limits of any shape always commute with each other. So, theorem 1 says that whenever limits of shapes I and J exist in a category C, then they commute with each other. And theorem 2, which is very important, like which limits, like limits will always commute with limits, colimits will commute with colimits, but which limits commute with which colimits. So that's a very important issue, and we are just going to answer this question in the category of sets. The proof is long, so again I am not going to cover it, but the idea is very important. Okay, it's a very deep theorem. So for any small category J, colimits of shape J commute in sets with finite limits if and only if J is filtered. So very powerful statement over here. See what we are saying, that with all finite limits, so especially finite products and binary equalizers, colimits of shape J commute with these two if and only if J is filtered. So filtered colimits have very important place in the category of sets because of its spatial shape, right? Okay, so I mean, you should look up the proof. It's in Maclean. Yeah, but I'm not going to cover the proof, but its idea is very important. As a corollary to theorem 2, we can say something more. Let alg be any category of finitary algebras. Yeah, for example, the category of groups, abelian groups, rings, R modules, lattices, etc. Yeah, So every operation should be finitary. Then so the first thing, there is a forgetful functor from any algebra to sets. So this forgetful functor creates small filtered colimits. And second thing, so small filtered colimits, small means set, J should be a set, the morphisms in J should be a set, small category, commute with finite limits in algebra. So this is not only the property of the category of sets, but it also gets pulled up to the category of algebras. And this is really important. I mean, I will show you the meaning of the word logical doctrine later on. Yeah, we'll put some limits and co-limits in two different classes, and then everything in this class will commute with everything in this class. That's called a logical doctrine. It's like orthogonal spaces, that every vector in this space is perpendicular to every vector in this space. A similar kind of strategy. Okay, so I will just want to, I want to give you an idea of how the proof works. Just a sketch. So we know that colimit of shape J of UD, like any diagram, you take D, D from J to alg, let's say. Then you can compose it with U, and then colimit of shape UD in sets commutes with finite limits. Definitely, because we are talking about the category of sets. That's what theorem 2 says. Okay, and hence inherits the algebraic structure of dj. The common algebraic structure of dj's. Now, if we have a binary operation, then what is that? Like, you are given a set A, then A square to A. A square is a categorical product, correct? A cross A. So what we are doing, that we are taking colimit of shape J of the underlying set, and then finite products commute. So therefore, colimit of UD square is nothing but the square of the colimit. Colimit of shape J will commute with binary products. So individually, in both components, you can take colimits and then take their product, or you can take products at every place and then take the colimit. Those two processes are going to give you the exact same answer. So therefore, you can define algebraic operations. So this is the use of products. Finite products, finitary operations. So they inherit algebraic structure of dj for for all j's. Whatever is the common algebraic structure, and moreover satisfies any equation that is satisfied by all dj. So for example, you have the property of associativity. Then associativity can be expressed as an equalizer diagram. you first take this operation, then you take another operation, or you, like the pairing happens, yeah, AB product is done first, then C is attached, or BC is done first, then A is attached. That's an equalizer diagram basically. So equalizer, again binary equalizer, so that's a finite limit, so it must commute with filtered colimit of shape J, and therefore it satisfies any equation, and that's why you can pull it up. You understand this idea? So this is the proof, and well, second, this is the proof for the first one, and second one, since U preserves finite limits, I mean it preserves all limits actually. We know that the forgetful functor preserves all limits and reflects isomorphisms. Yeah, I mean it is conservative. This is the name for it, this property. Yeah, we get the commutation, we get 2. Yeah, I mean required statement. So we don't have to do any extra work, we just needed that this creates small filtered colimits. However, like in the category of sets, you can ask, like, is this distinction between filtered colimits and finite limits, is that spatial? Can we dualize the whole situation? So for example, if we take the opposite shape of a filtered category, we can call it co-filtered, then will the limits of co-filtered shape commute with finite colimits? That's the dual statement, and the answer is no. Okay, it's very specific to the category of sets itself. So now here is an example. So I will write in a different color. So filtered colimits do not commute with finite limits in the opposite category of sets. Okay, so we are just writing it without using the word co-filtered. Okay, so now you consider this particular diagram, n, 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 and dot dot dot, and this is the shift map, and here it is 1, 1, 1, and well, I don't need to describe the rest of the maps. Yes, all the maps, other maps are evident, these are the unique maps. Now what is the, like, is every map in this diagram, every vertical map, that is surjective? Yes. So therefore it is an epimorphism. Okay, so every vertical map is an epimorphism, but if you take the limit of the top row, what is it? It is the empty set. Yeah, because nothing comes via shifts. Every element has got a finite history, so therefore it will cease existing beyond a certain point in the past. Okay, so therefore the limit of the top row is empty, and the limit of the bottom row is 1. That's the identity map, and this map is not epimorphism. Okay, not epi. These are epis. So the co-limit, the limit of epimorphisms, the co-limit of epimorphisms is not an epimorphism here. Okay, sorry. No, it's a limit by, It's the limit. Yeah, because this is, we are, okay, I should say that we are looking at the diagram in the category of sets, but we are treating it as if it's in category sets op. So therefore, the co-limit of the top diagram in the category sets op is empty, and the co-limit of the bottom row in category sets op is 1. So therefore, the co-limit of this sequence of epimorphisms is not an epimorphism, but epimorphism is associated with pushouts. Yeah, because pullbacks are defined using, like monos are defined using pullbacks. So similarly, epis are defined using pushouts. So that means that this co-limit doesn't preserve pushouts. So it doesn't epis. So it doesn't preserve pushouts. Simple. Okay. So this is the whole idea behind this. That it's a property of the category of sets itself, and not beyond that. Okay, so now we can start utilizing this particular part. Yeah, I mean this particular property. So here is an important definition. So say that, suppose, yeah, C is a locally small category. I mean, henceforth, all the categories that I consider in this lecture are locally small and with filtered colimits. Okay, so say that f from C to D is a finitary functor if it preserves filtered colimits. Okay, so finitary. So you can see that we are beginning to talk about the notion of finiteness. Say that an object A of C is finitely presentable if the obvious functor associated with A, which is the home functor from C to sets, is finitary. Okay, so an object is finitely presentable. Have you heard this term finitely presentable before? In algebra? Have you ever heard this term? No? Finitely generated, have you heard? Okay, so finitely generated means there is a finite set of generators. What is finitely presentable? It means there is a finite set of generators as well as a finite set of relations between those generators. So finitely presented and is finitely generated plus finitely related. Now, explicitly mentioning the generators and relations, now that's a different process, and this particular statement is saying that you just have this representable functor has to preserve filtered colimits. Yeah, this is the important issue. I mean, of course, if there are two names, then it's not always the case that they may mean the same thing. But in algebra, these two things mean exactly the same thing. Okay, so, and this is a categorical description, so you can go beyond the category of algebras. So for example, in the category of sets, A is finitely presentable, FP for short, if and only if A is finite. Okay, so let's look at this particular proof. So suppose A is finite. with cardinality of A equal to n. Then sets A blank is what? It is isomorphic to blank to the power n. If it is a 2-element set, then you take square. And why does it why does it preserve filtered colimits? Because it's just a finite product, and finite products are finite limits, and finite limits commute with filtered colimits. Okay, so therefore, since blank n is a finite product, it commutes with filtered colimits. And the forward implication, yeah, I mean commutes with filtered colimits is same as preserving if we treat it as a functor. And conversely, if A is finitely presented, then what will happen? Then write A as express A as colimit of this shape of, I mean A prime in this and colimit of this. Yeah, if you take this diagram, then what will happen? And use that sets A, then this colimit, yeah, A prime in P fin is in and use that this is in bijection with the colimit taken outside. Yeah, so colimit of A prime in P fin A. Okay, what is this colimit inside? It's just A. So in particular, the identity map A to A, yeah, this must factor through some finite A prime. When can this happen? Because every map here should appear in the colimit. Now let me remind you, we have talked about this earlier, that colimits of shape n is all about the things which eventually appear, the foreseeable future. Yeah, if something starts appearing, then it will continue to appear in the future. That's how we visualize colimits. But here also we are doing the same thing. A prime is a finite subset, and now we have a diagram of these home sets, yeah, A to A prime for different things. And then what are the maps? Like, can you imagine what is happening? Like, see, here we have sets A1, then we have sets A2, then we have sets A1 union A2, A comma A1 union A2, and so on and so forth. Like, this is a directed diagram, so eventually everything comes together. Now the identity map must also appear at one of these locations so that it will continue to exist under these inclusion maps. No, that's not a disjoint union. I said colimit, it's a directed colimit. It's not disjoint. Directed colimit, I mean, you understand the idea of colimit? Why are you saying disjoint union? It's disjoint union quotiented out by some relations. Okay, so eventually like things are coming together. So identity map must also appear at this point. Like you can see that these are all monomorphisms. Are you convinced? These are all inclusions. Yeah, it's just extension of codomain maps. So therefore, the identity must appear somewhere and then it will continue to exist until eternity. Yeah.
So the relation is of bijection, not equality. So maybe the identity does not appear, but something else appears.
No. It's a bijection, but actually, like here, because we are talking about sets, if you choose a proper representative of A primes, then it will be equality. So the identity map must factor through one of them. It must appear at one of these locations and then it will continue to exist because nothing gets killed eventually. Every map is inclusion. So it's just extension of codomain. So therefore, the identity map must factor through some finite A prime, and what does that mean? And hence A itself is finite. Yeah, A equals some finite subset of A. Yeah, so that's the idea here. So like this eventual future, yeah, that is the main idea of directed colimits. Things start happening and then they will continue to happen. Yeah, whereas for limits, the co-directed limits of shape n op, what did we see? That things happened in the past until a certain point and then they cease to exist. So directed colimits are important in this sense also. Okay, so now one important thing, like in sets, a set is finite if and only if it is finitely presentable. Moreover, we saw that every set can be written as a directed colimit of finite sets. Yeah, because you just take P fin x. So essentially what you can say, up to directed colimits, the finite sets control the entire category. You understand this idea? So it generates the whole category. So let me write this as a definition. Say that a locally small category C is a locally finitely presentable category, in short LFP, if it is maybe I should write all the properties. If C is co-complete, okay, then another thing is that it should have, there is a set of isomorphism classes of finitely presented objects of C. Okay, and finally, every object of C is a filtered colimit of a diagram of finitely presented objects. Okay, I mean is up to isomorphism, obviously. You understand this? Yeah, that up to isomorphism, every object is a filtered colimit of finitely presentable objects. So obviously you know one example now, the category of sets. Okay, so for example, sets is an LFP category. Okay, we want to look at more examples, but let us take a moment to understand what this really means. The collection of all finite sets up to isomorphism is just the set of natural numbers, and that is a set. Okay, so that's the second condition. And every object is a filtered colimit of finitely presentable objects. So you can build. Directed colimits are the most useful way of building things with patches. You patch this, then whenever they two have the same identity, then that means like there is a common patch. Then you go on building a more complex object. In this whole lecture, I have used the word finitary sometime. So let me highlight all those occurrences. So look at this. The first definition of a filtered category. If for any finite category I and a diagram D has a cone under it, I can replace finite, which is less than aleph naught, by less than kappa for any kappa. Yeah, so I will get a different thing. Then we will say that a functor is kappa-Ari if it preserves all kappa-Ari filtered colimits. Kappa-Ari filtered colimits are the colimits of shape kappa filtered categories, right? Then an object is kappa presentable if this functor is kappa-Ari. So everything will work, and we actually get back the concept of cardinality essentially within the category theoretic framework. Okay, and then this example, which is a theorem itself, like proposition, that a set is kappa presentable if and only if its cardinality is less than kappa. Everything will work. Yeah, and similarly you can define locally kappa presentable category. Yeah, so the ball of size less than kappa generates the whole category under kappa size colimits, kappa filtered colimits. In general, like if you replace finitely by kappa, any kappa, like aleph naught by kappa, then you call it a locally presentable category. And there is also some literature where you relax the first condition in this definition, C is co-complete, by C has filtered colimits. Yeah, and you get the definition of finitely accessible category. So the reference for all this material is, as the name suggests, locally presentable and accessible categories. This is by Adamek and Rositsky. Yeah, this is the book. It's a monograph on this topic. I'm just scratching the surface of it in this lecture, not doing much. So these are important classes of categories because of some theorem. It's a celebrated theorem of Gabriel and Ulmer from 1970s. And I will present that theorem, but before that we will look at some more examples so that you will be convinced why I mean, this particular property is important. Okay, so one more example. Any category alg of finitary algebras is also LFP. Okay, so locally finitely presentable. Now here is what the proof is. I mean, I'm not going to describe the whole proof. The proof is long, but one side, like, you had to first understand what are the finitely presentable objects. Yeah. So any algebra, so suppose f generated by x1, x2, xn is a free algebra generated by n generators. You understand free algebra? You close it, you have n indeterminates, they have no relations between them, and you generate the algebra. Free group on two generators. Yeah. So same thing. You only take those axioms which are absolutely necessary, otherwise you don't choose them. Okay, then alg, the home set in alg of this comma a is isomorphic to a to the power n. Same argument as before. There are n generators, so it just takes n array copies. So obviously, and hence by above corollary, is finitely presented. Yeah, so free algebra generated by n generators, they are finitely presented because it's simply a product, finite product. So finite product commutes with filtered colimits even in the category of algebras. Okay, so moreover, yeah, I mean,
Can do something like the
finite power set and take finitely presented subalgebras. Yeah, we will get there. Moreover, if B is finitely presented algebra, i.e. Finitely generated plus finitely related. Okay, then alg from B to A is, I mean, isomorphic to the set of all A bars in A to the power n, where n is the number of generators of B, such that the relations Ri A bar hold for all I. Yeah, I mean, these are relations. So for example, associativity, commutativity. So these relations hold for all those tuples. And well, what are relations? Relations can be expressed in terms of equalizers, and therefore, yeah, therefore B is also finitely presented object. Understood this? B is also a finitely presented object in the category of algebras. Yeah, the converse is much harder. Yeah, converse is hard, but it's true that given any finitely presentable object, then you can show that it is finitely generated and finitely related. Okay, so this is one part that we have found what are finitely presentable objects. So finite generation and finite relations. So ultimately up to isomorphism there is only a set. Yeah. So therefore, I mean, this is how we write alg FP. Yeah. This set of the collection of isoclasses of finitely presented objects is a set. Yeah, because it has finite generators and finitely many relations. At a time you just have to choose a set. So countable union of countable sets is countable. Yeah, that's the argument we are using here. Moreover, yeah, I mean, okay, so finally, obviously, I mean, the category of algebras, finitary algebras, is co-complete. Limits and colimits, they are created by the forgetful functor. So therefore, nothing to worry about that. Okay. Sorry, colimits are not. Limits are created. Actually, in the definition of locally finitely presentable category, we can also take completeness as the criterion, completeness or co-completeness. Yeah, but I can assure you that the category of algebras is co-complete. I will tell you the reasons. I don't remember it right now. Next time I will tell you the reasons. Okay, so finally, yeah, every algebra can be written as a directed colimit of its finitely presented subalgebras. You take any finite number of elements, actually, I mean, how you generate, like, I shouldn't say okay, I should say colimit of its subalgebras with finitely many generators and relations. Okay, so this is the main point here, that even algebras you can generate only because all the operations are finitary. That's all.
Like those will not necessarily be sub-algebras.
Yeah, they are not necessary. Okay.
You will be taking some generators and some
Okay.
operators.
I think with finitely many generators and relations.
By the algebra generated by finitely many. Yeah. Okay, fine. But you can always construct that diagram. By the algebra generated by finite subsets. Maybe I should write it again. And imposing only finitely many relations. Relations at a time. Okay, so that's how you show that the category of algebras is also locally finitely presentable. However, in the category of topological spaces, yeah, so this is a non-example. In top, X in top is finitely presented if and only if X is finite and discrete. So therefore, you can never write a sufficiently complex topological space as a directed colimit of finite discrete subspaces. That's just useless. Okay, so top is not locally finitely presentable. In fact, top is not locally presentable at all for any kappa. Okay, so well, one more thing which I believe is a good exercise. So this is an exercise, you should try it. If C is small, then CC blank belonging to C sets are finitely presented. Try this. Yeah, all the representable functors are finitely presentable objects. Okay, so now we are going to approach the main theorem, Gabriel-Ulmer theorem, duality, Gabriel-Ulmer duality. Yes.
The exercise, they are the only finite.
No, I did not say that. In fact, your question is relevant to next result, that any finite colimit of finitely presentable objects is again so. Yeah, so you can take direct co-products, finite co-products and co-equalizers, etc., and that will again be true. Any questions? Okay, so yeah, I mean, you need this co-completeness property as well. Yeah. So for example, if you just take the restricted category of sets, you don't have axiom of infinity, so just the category of finite sets. Now that is not co-complete. Yeah, like externally we are assuming axiom of infinity, of course, so that's why it's not co-complete, so it's not locally finitely presentable. So you need to take the full extent, but actually there is a very good representation theorem. There are several versions of it, but I'm just going to present the one which is accessible for this class. That a category C is an LFP category if and only if it is equivalent to the category of to a full subcategory, full reflective subcategory of the functor category A sets for some small a, small category A, and that is also closed under directed colimits. Okay, so maybe I haven't written the English properly, but I want to say three things here. That it is equivalent to some category which is a full subcategory, it is reflective, and it is closed under directed colimits, which means the inclusion functor preserves directed colimits. Yeah, inside some functor category A sets where A is small. I mean, if these categories are known as pre-sheaf categories. Yeah, they have very nice properties. They are toposes. We'll see what a topos in a future lecture. So these are full reflective subcategories of toposes, pre-sheaf toposes under directed colimits. Closed under directed colimits. Yeah, I mean, this is a structure theorem. Representation theorem means it's a structure theorem. You understand all of them at the same time. And based on this, like, we can approach the main theorem, which is Gabriel-Ulmer duality in 1970s. Okay, so let me write the statement first and then I will explain what it means. So it's a duality. We have already seen what is a duality. It's an equivalence between C op and D. Okay. And here I am writing two functors. Well, technically they are not functors. I have to explain lots and lots of things in this particular expression, but there is a duality. Yeah, this is Gabriel-Ulmer duality where, okay, so first of all, we have to talk about two categories. So two categories means categories whose objects themselves are small categories. We have already seen one such example, CAT with small at. Yeah. Or, I mean, the objects can themselves be large categories as well. It doesn't matter. It's just that their objects are categories and the morphisms are functors. So now you have a zero level thing, like the objects of the objects are the actual objects, then one level thing which is the categories, and then the two level category. Okay, so here cart is the two category. This is not a like proper definition, but you understand what I am saying. Is the two category of small Cartesian categories and Cartesian functors between them. Okay, so cart is the two category of small Cartesian categories, and okay, Cartesian you understand? Finite limits. So they are small categories which have finite limits, and the functors preserve finite limits, functors between them. Okay, this is the first thing. Okay, then LFP is the two category of all LFP categories and functors between them that preserve all limits, all small limits and directed colimits. Cartesian functors are the functors which preserve finite limits. Yes, correct. And LFP functors are like morphisms between two LFP categories are those which preserve all small limits and directed colimits. Now, this is not an arbitrary choice that I am talking about here. First of all, like if you forget about the size condition, then sets is a cart category. It's a Cartesian category, sets has finite limits, and then cart blank sets, what does it say? It says that take a category, small category, let's say C, and then map it to the set of the category of all Cartesian functors from C to sets. So finite limit preserving functors from C to sets. that will be an LFP category. Now, why is it an LFP category? It's thanks to representation theorem. Because we are talking about all functors which preserve finite limits, so such a category will be isomorphic to, let me write this bit. Given any Cartesian category D, cart D sets is a full reflective subcategory of the functor category D sets and is closed under directed colimits. Why is it closed under directed colimits? Because all these functors preserve finite limits and finite limits commute with directed colimits. So therefore, this happens. So thanks to representation theorem, this is actually happening. I have not given you full details. Like, you can see that it is a full subcategory, obviously, and it's closed under directed colimits. But why is it reflective? You have to do a little bit of work for that. But okay, and similarly, like sets is an LFP category. So therefore, all functors from an LFP category L to the category of sets, that should be a small category. So here also, like one phrase that I always like to say, that LFP categories are large, but they are not too large. They are still generated by a set, the set of finitely presented objects. So they are large but not too large. So therefore, when you put too many restrictions, that it should preserve all small limits, all directed colimits, it's lot of restrictions. So actually, the ultimate result becomes a small category. Here there is only one more thing remaining to say, that sets is called a dualizing object. This is a duality, and I am talking about a dualizing object. It's a category which occurs in both worlds simultaneously, and it's a dualizing object because the functors are always blank sets in both directions. These are equivalences. And okay, no, there were two things to say. And here I can talk about the Cartesian doctrine, that on one side I have got finite limits. This is a term by Mackay. Logical doctrine is a term by Mackay. So finite limits, and on the other side we have got all small limits and directed colimits. Now observe that if you take anything from the first class, then it commutes with anything from the second class, and these are the maximal such set classes. Finite limits commute with all small limits because limits commute with limits, and finite limits commute with directed colimits because we have seen that happens in category of sets. That's a theorem we did not prove. But the theorem said something more. It said that any shape J, the directed colimit of shape J, for any shape J, colimits of shape J commute with all finite limits if and only if it is filtered category. So therefore, these two classes, they are perfect for each other, and this property is called a doctrine, and it's called Cartesian doctrine because Cartesian logic, the left hand side of Gabriel-Ulmer duality, it is the syntax, and the right hand side is the semantics, categories of models of Cartesian theories. Okay, I'm not going to go into details of that because this is not a logic course, but there are different doctrines for different types, different fragments of logic, where you add more things on the left hand side and then the right hand side shrinks. Okay, let's stop here.